Dark matter is currently thought to make up approximately a quarter of the universe, with visible matter at 4% and dark energy accounting for the rest. Its existence is now generally accepted in the physics community and considered to be a vital part of our understanding of the universe. The first to consider such a notion was Swiss physicist Fritz Zwicky at the California Institute of Technology all the way back in the 1930s. Zwicky noticed that the measured orbital speed, calculated from the amount of measurable mass, was expected to be significantly higher. He concluded that there must be some sort of dark matter, defined as matter that does not emit light, and hence it was that was responsible for the apparent missing mass. His published works were not taken too seriously, as at the time people's understanding of galaxy clusters was rather shaky. It wasn't until the 1970s that Vera Rubin, an American scientist, shone light back on to the mysterious issue of dark matter. Her work involved examining individual galaxies' speeds, which were still found to be too fast. This time it was harder to brush off the evidence for the existence of dark matter, hence leading her work to bring back in the interest of physicists to this theory. Now that we know how we got here, let's examine the actual proof. One proof for dark matter lies in the motion of stars within their galaxies. This motion can be best described with the help of rotation curves, which are graphs plotting the orbital speeds of the stars around the galactic center against their orbital radius. For example, if the galaxy would rotate like a disk, the orbital speed would increase linearly with the radius. However, galaxies are not solid disks. Gravity holds things in orbit. Things with a greater mass have a greater gravitational force, hence greater orbital speed. If we looked at all the luminous matter, it is mostly concentrated in the center of galaxies. Based on this observation, it follows that Kepler's third law applies, i.e., that the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. This would, however, produce the following graph. However, experimental analysis produced the following pattern. Comparing the experimental results to the predicted pattern, it is clear that Kepler's third law is not an accurate model for the motion of stars in a galaxy. So why? One explanation could be that, in fact, our initial axiom, that galactic matter is concentrated at the center of the galaxy, is wrong. Now, by equating the circular motion of a star in the galaxy to the gravitational force, we can calculate the mass of the galaxy. Using the experimental values taken, it was found that the predicted mass of the galaxy was in fact 10 times larger than the visible mass. Therefore, this invisible matter with high rotational velocity must exist throughout the galaxy, especially on the outskirts, and not emit any light. Hence, dark matter. Further proof: gravitational lensing. In space, rich clusters of galaxies exist. Due to their large concentrated mass, such clusters act as gravitational lenses, bending space-time to enable us to see light from background galaxies. What we see are the distorted arcs of galaxies very far away, and it is these arcs that demonstrate the effect of lensing. However, observations and the following calculations reveal that the lensing caused by the clusters was far more than expected based on their visible mass. It appeared that much more matter should exist, also interacting with light and bending space-time. X-rays and intergalactic gas. By measuring the temperature of the gas based on the X-rays emitted, the gas pressure can be estimated. The gravitational attraction calculated suggested the mass larger than the visible mass of the gas should be present. Based on the evidence from rotation curves, gravitational lensing, and X-ray emissions, there is a significant amount of support for the existence of dark matter. The prediction of such a substance provides an explanation for our apparent lack of mass, and the quantities of dark matter predicted from each piece of evidence are all approximately 25%. The next key step in physics research is to experimentally detect dark matter, and hence prove its existence true.